Inside your phone, your computer, pretty much everything you use, there's this invisible science that has completely reshaped our world. It's really the story of a special kind of material that we've figured out how to teach to think. So today, we're going to pull back the curtain on the semiconductor. To really get a feel for the scale of this revolution, you just have to look at this. On one side, you have the 1945 ENIAC computer. This thing was the size of a house, okay? It used 18,000 vacuum tubes just to perform about 150 operations per second. Then, flash forward to 1990, a microprocessor packed over 1 million transistors into a space smaller than your thumbnail, and it could perform 20 million operations per second. I mean, this isn't just an improvement, it's like we jumped into a different dimension. So yeah, that brings us to the big question for this whole explainer. How on earth is that even possible? What was the breakthrough that let us shrink a house-sized calculator onto something smaller than a postage stamp, and at the same time make it millions of times more powerful?
Well, the answer isn't just about, clever engineering or figuring out how to make smaller wires. It was a genuine miracle of material science, a discovery of a special class of materials that could be taught to think.
Okay, so to understand this materials science miracle, we first need to take a quick look at how different materials handle electricity. At a really fundamental level, they kind of fall into three distinct categories.
The heroes of our story are found in a very specific neighborhood of the periodic table, right here in column IV. This is where elements like silicon and germanium live. And the thing is, they aren't great conductors, but they aren't great insulators either. There's something really special right there in between: semiconductors.
This visual shows us exactly why they're so different. Think of it like this. Electrons need to jump from a home base, that's the valence band, onto a freeway, the conduction band, to create an electrical current. In a conductor, on the right, the base and the freeway are basically connected. Electrons just flow, no problem. In an insulator, on the far left, there's this huge chasm, making it almost impossible for electrons to cross. But a semiconductor, right in the middle, has a small, manageable gap. It's this gap that makes them so special.
So you can think of that energy gap as a hurdle. For an insulator, that hurdle is impossibly high. For a conductor, well, there's no hurdle at all. But for a semiconductor, the hurdle is just the right height. With a little push, we can coax an electron into jumping it. And that ability to be controlled, that is the key to everything. But here's the thing. A perfectly pure semiconductor is almost an insulator. On its own, it's not actually very useful. The real genius, the absolute game changer, came when scientists figured out how to precisely manipulate its conductivity. This is the secret that unlocked its incredible power.
So this is what pure or intrinsic silicon looks like at the atomic level. Every atom is perfectly bonded to its neighbors. All of its outer electrons are locked in place, holding hands in what we call covalent bonds. There are no free electrons to carry a current, which means it's a very, very poor conductor. The secret ingredient is a process called doping. Now, I know it sounds a little illicit, but in materials science, it just means intentionally sprinkling a few impurity atoms into that perfect silicon crystal. And this carefully controlled contamination is exactly what turns a useless material into a revolutionary one. And here is exactly what that doping does. On the left, you see the perfect, pure silicon. But on the right, we've swapped out just one silicon atom for a phosphorus atom. Now, silicon has 4 outer electrons to bond with. Phosphorus has 5. So after it bonds with its 4 neighbors, there's 1 electron just left over. This free electron can now move around and carry a negative charge. We've just created what's called an N-type, or negative, semiconductor.
So we can add impurities to create this N-type material with extra electrons. But what if we add an impurity with 1 less electron? Well, that creates a hole, a spot where an electron should be, and we call this P-type, or positive material. Now, the real magic begins when we join a piece of P-type silicon right next to a piece of N-type.
This is called a p-n junction. And as soon as the two types touch, the free electrons from the N side rush across the boundary to fill in those holes on the P side. This creates a thin, electrically neutral area right at the junction, which we call the depletion zone. This zone acts like a barrier, preventing any more electrons from crossing over. A natural wall has formed all on its own.
Now here is the crucial point. We can control this wall with electricity.
If we apply a voltage in one direction, we call it forward bias. We shrink the wall and let current flow right through. But if we reverse that voltage, reverse bias, we make the wall wider and thicker, blocking the current completely.
By doing this, we've created a fundamental component called a diode. It's a perfect one-way gate for electricity. It allows current to flow forward, but it slams the gate shut if that current tries to go in reverse. This simple little gate is the absolute cornerstone of all modern electronics. And this simple one-way gate is the microscopic building block that takes us all the way back to where we started, from the house-sized ENIAC to the chip in your pocket.
So by layering these p-n junctions, scientists at Bell Labs created the transistor back in 1947. Think of it not just as a gate, but as a microscopic, ultra-fast switch. And from there, the pace of innovation was just breathtaking. In '58, the first integrated circuit put a few of these switches onto a single chip. And just a little over a decade later, in 1971, Intel's first microprocessor put thousands on a single chip. This exponential progress was so consistent, it actually got a name: Moore's Law. Intel co-founder Gordon Moore observed that the number of transistors we could fit onto a chip was doubling roughly every 2 years. Now, it wasn't a law of physics, but for decades, it was the relentless heartbeat of the entire tech industry. And that brings us to today. The microprocessor at the heart of this circuit board doesn't contain thousands or millions of transistors. It contains billions. Billions of those tiny one-way gates and microscopic switches, all built from carefully doped silicon, all working together to perform trillions of calculations per second. That is how you shrink a house into a chip. The ability to control the flow of electrons through a cheap, abundant material like silicon completely remade civilization in a single lifetime. It's really a testament to human ingenuity, which of course leaves us with one final thought. What material, what discovery is just waiting out there to do it all over again?